Welcome to Discrete Structures. We're doing section 3.1 today, which is about relations. Okay, this is Noson Yanofsky. Okay, so let's go back what we started with. This is a new chapter, so it's a new idea. So chapter 1 was all about sets, and we loved sets. We talked about functions between sets, etc., etc. Okay, chapter 2 was logic. It has nothing to do with this. Chapter 3 is about relations. Relations are more general than functions. They're better than functions because they can do more. Functions are special types of relations, but we can go much further. So let me tell you what a relation is. Okay, definition. Okay. Given sets S and T. It's a little bit dark in here. Hold on. Given sets S and T, we don't want to talk about a function from S to T, but rather we want to talk about a relation from S to T. So a binary relation, binary as in two, binary relation from S to T is a subset of S cross T. Okay, so let's just remember what S cross T is. S cross T is a bunch of pairs of elements from one in S and one in T. Okay, now a relation is some of those elements, not all of them, some of them. Okay, and so we're gonna spend time talking about that. So this is called a binary relation. It relates one set to another. Okay, now the examples you'll see will be perfect. So let's talk about it. So let's talk about an example. So you run a business, okay, and you have a set S consisting of customers. Okay, you keep track of customers. You have a set T, okay, now of products. These are the products you sell. Okay, and then you have R1 subset of S cross T. So you have a relation. The one just means it's just an example. You know, R1, R2, R3, you can have R, whatever you want. It's a subset of S cross T. And it's going to be some of the pairs of S cross T. And which pairs do you want? So you will say as follows. X comma Y is a member of R1 if customer X, if X bought Y. Okay? So if X bought Y. If one customer bought that thing, then you put it in the relation. Okay, and this is called relation. This is the beginning of relational databases. Relational databases is all about businesses. Databases all starts with this concept. So this is very important. You want to say hello to the camera? Okay. Okay. This is my daughter Miriam, and she made some beautiful things. But right now, she's going to go upstairs. Wow, it's beautiful. Okay. Bye-bye. So, X comma Y if X brought Y. Now, the main point is it's not a function. Why? Because each customer doesn't only buy one product. They buy many products. So it's not a function from S to T because one customer can buy more than one product. It's also you can have customers that buy no products. We didn't have that. Functions are usually from S to T, assigns to every guy in here, a guy in there. So this is more general than it. It can have one customer can have many products, and more important, one product can have many customers. Okay, and dealing with this is what happens all the time. So here's a typical relation. Okay, so every business keeps this type of data in mind because they want to, if they have a sale of a certain type, they go to the customers that bought those type of things and they send them advertisements and things like that. Okay, so all of databases starts off with this concept. Great. Let me give you another example that's more close to your heart. Okay, X, you have S is equal to Brooklyn College students. You have T equal Brooklyn College courses. Okay, and then you have a relation between them. So let's call it R. Let's just call it R. Okay, R is a subset of S cross T. Now, I want to tell you what elements are in R, what elements are not in R. Okay, so I'll say X comma Y is a member of R if X is enrolled good Lord, enrolled in Y. Okay, so maybe this should be classes, not courses. Classes. Okay. Now Brooklyn College keeps such a relation in their computers because they want to know who's taking what courses. Okay, and let's just go through it. One student is usually taking more than one courses, so it's not a function, and it's not a function this way. Not every each class can have more than one student, or usually does have more than one student. Okay, so Brooklyn College has to maintain such a thing in their computer, and let's just do another example. S is equal to U.S. states. Okay, T is equal to U.S. citizens. You know what? It doesn't matter. I can U.S. citizens. Okay, and what do we say? We say as follows. We'll have a relation between them. Let's call it R3 for this. Okay, and it's S cross T. Okay, now some of those things will be in there. Some of the things will not be. Some ordered pairs will be there. Some of them will not. And so you say as follows: X comma Y is a member of R3 if X, that's a state, if Y visited if Y citizen visited X. So have you ever been to North Dakota? Okay, so let's put it in. Okay, so me, that's me, NSY, oh, sorry, North Dakota, okay, NSY, I have never been to North Dakota. Conclusion, I am not in R3. Me visiting, however, I did visit Montana. So NSY, Montana, okay, it is in R3. Okay, and you can make a list. I have a friend who works in a travel agency, and she has been working there for 20 years, and whenever she can, she goes to a different state. She wanted to go to all 50 states, and last year she treated her parents, she and her parents went to Alaska because that was the last state she had not seen, so she saw every single state. Okay, so she would be the entire thing. Great. Okay, let's do another one like this. Same states and citizens, okay? And so we'll make another relation about the same thing. So we'll call it S cross T, just like before. But here, oh, we have S to R3. Let's make another relation called R4. What's the difference? And we say X comma Y is a member of R4 if Y lives in X. Okay. Now that's interesting because you can only live in one state. Okay, I'm not talking about people who have a house, you know, what's their primary residence, we'll say. Okay, so this is an interesting relation because this is actually a function. This is a function from T to S. Because every single person has one state, exactly one state. Every single U.S. citizen has one state who's his primary residence. Let's assume there's no expatriates or something like that, people who moved out of the country. Okay, so that's closer to what a function is. So again, that's a special type. But visited, we've all visited many states, but we only have one primary residence. Okay, great. Okay, and the reason why I'm showing you this, I'm showing with two of the same states, you can have different types of relations between them. Okay, and so we can write these things in different ways. So if R is a subset of S cross T, we can write X comma Y is a member of R. This is just different notations that the book uses. Okay, you can say X is R related to Y. You can say X R Y, and then it's also you can say this X tilde, that means kind of the same with respect to Y. Okay, so these are 4 different ways of saying the same thing, and you got to get used to the notation of all 4 of them. Great. Okay, great. Okay. Now, I want to get closer discussing what's the relationship between relations and functions. Okay? And I can tell you right now, you have relations, and then you have special types of relations called functions. And I showed you one just now about living in a state. That was a function. So that describes a certain function. Okay. So, but I want to be a little bit more carefully, okay? And so be more careful. So I want to just remind you of something that we saw. Let f be a function from S to t. Then here's something we saw in chapter 1. Graph of f we're going to write that as R sub f. Okay, R sub f. Okay. It's equal to, we saw this before, it's equal to x comma y such that member of S cross T, member of S cross T, such that dot dot f of x is equal to y. We saw that. Okay, so let's just give an example. If f goes from the real numbers, let's do the real numbers to the real numbers. Oops. Real numbers to the real numbers. There's a typical function that we saw. I'm worried about, you know what, let's do n to n. So we don't have to deal with the r. And we have f of n equals n squared plus 3. So f of 1 is equal to 1 squared plus 1 is equal to 4. And f of 2 is equal to 4 plus 3 is 7. And f of 3 is equal to 9 plus 3 is 12. Okay, so what we can say is, ready? 1 comma 4 is a member of the graph of f. 2 comma 7 is a member of the graph of f. And 3 comma 12 is a member of the graph of f. Okay, so here's nice examples of that. Okay, so let's just reiterate. We saw this already, but the main point is that the graph of f is a subset. Oh, but let's just do this. 3 comma 13 is not a member of Rf. Okay, because if you plug in 3 into here, you're not going to get 13, you're going to get 12. Okay, and 4, if you plug in 4, you're going to get 16 plus 3 is 16 plus 3 is 19. So 4 comma 21 is not a member of Rf. Okay, The main point is that graph of f is a subset of S cross T. Great. Okay, great. Okay, so let's just remember what we have. If you're given a function, you can get a graph out of it. Now I want to go the other way around. I want to ask the following question. If you're given a subset of S cross T, is it the graph of a function? Okay, I just want to say, if a functions, you can think of functions as sitting inside relations because for every function describes a graph, and a graph is a type of relation. But now I ask the following question. When is a relation a graph of a function? Question. Let me say it again. Okay, here's relations, here's functions. Okay, so let me ask you the following question. If I give you a relation, how do you know if it belongs in here or it belongs out here? Okay, and we actually did this when we were talking about functions and relations and graphs. And we talked about special cases, what we have. Okay, and so I can already give you the answer. R subset of S cross T. So this is the question. When is a relation a graph of a function? R subset of S cross T is a function, is a graph of a function if for each, I'm going to say little s member of S, comma, there is exactly one y member of T. I don't want a y. I want little t member of T. Okay. With S comma T member of S cross T. Okay, so this makes sense. Okay, let's just go through it. If there is none, then it's a relation, it's not a function. But if this is true, then for every S there's exactly one T that matches up, then you have what's called a function. Okay, great. So that takes care of that. Let's just talk about some other things we can talk about. You can also have, this is for a binary relation, S cross T. You have R, a subset of S cross T. That's a binary relation, two-ary. But you can also have something like this. You can have set S1, S2, and S3. You can have three sets, okay? And you could talk about subsets of them. R. So this is R, a trinary relation. It takes into account three things. And again, all of databases deal with this. So you might have, a database might have a customer's name, products that they buy, what state they live in, okay, or what state they visited your store. Okay, so if your customer is that goes into Bed Bath and Beyond, you want to know which states they visited, and you want to keep that all that information. Okay, so that's called a trinary relation. But there's also S4 all the way till S9n, and then you call that an N-ary relation. And again, all of databases is dealing with this. You might talk about matching clothes. So for example, I'm talking about men here. You have a shirt, you have a pair of pants, and you have socks. Okay? Now, you can't just wear anything with anything. There's a subset of shirts, pants, and socks, okay, all ordered pairs, all ordered n-tuples of them, such that those match and you can wear them. Okay, and this is something that certain people, who shall remain nameless, never understood this stuff. Okay, so by me, everything matches. I never understood this, but we're not talking about me. Okay, so we can talk about that. Great. So that takes care of that. Okay. Let's stop here for a second. Okay, so now that we know what a relation is, we're going to talk about special properties of relations, and we're also going to talk about a special type of relation, not a relation between one set and another set, but a relationship between a set and itself. In other words, we're going to talk about how elements in a set are related to themselves. You'll see 11 examples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 examples. I think 11. Okay? Maybe even more. So don't get nervous. Okay, so we're going to talk about R, a subset of S cross S. Okay? And that's going to tell us how the elements of R of S are related to each other. Okay, so let's do some examples. Okay? We're going to do examples. Okay? R, subset of people cross people. Obviously, first few examples we're going to do are more jokey, and then we're going to get into more mathy types of examples. Okay, and we say X comma Y is a member of R, or they're R related, or they're related, if X is a sibling of Y. So, two people. And we want to know, are they siblings of each other, yes or no? Okay, that's a nice example. I want you to do the following for your notes, because we're going to come back to all these examples. I want you to make the following list. R, AR, S, AS, T. Okay. These are, I'll explain to you later when we do it, but in your notes I want you to make this next to it. These are 5 possible properties that this relation has. We're going to go through them later on, but I want you to write them in now, and then later on we're going to make checks and X marks. Sounds good. Okay? Another example. R, subset of people cross people. Okay, so we want to know how people are related. Okay? X comma Y is a member of R if X is dating Y. Okay, and again, put in R, AR, S, AS, T. So we'll go through that later on. Next, R, subset of U.S. citizens. Again, all these examples are mine. They're not the book's. U.S. citizens. Okay, you have citizens cross citizens, and we have as follows. X comma Y is member of R if X and Y live in the same state. Okay, nice examples. Okay, I just want to make sure that I can see what's down on the bottom. Great. Okay. How do they are? R, AR, S, AS, T. Okay, good. Next, let's do another example. R, subset of the following set. 0, 1, 2, 3, cross 0, 1, 2, 3. Okay, I got to tell you what the relation. This is a 4-element set. That's a 4-element set. We say x comma y is a member of R if and only if, or if, okay, x is less than or equal to y. Okay. Okay, let's do this. R, AR, S, AS, T. You'll understand later what those means. Okay, great. One more example. We're going to have a few more examples later on, but one more example, then we'll start talking about the properties. How about this? Same set. Oh, by the way, we can sit down right now and we can write what this subset is actually equal to. It pays to do that for a second. What is this subset equal to? And I'd like to show you. In other words, what is this relation? Well, this relation is 0, 0. 0, 1, because 0 is less than or equal to 0, 0 is less than or equal to 1, 0, 2, 0, 3. All these are elements in the set, so R equals all these things. Next, what else? 1, 1, 1, 2, 1, 3. Okay, what else? 2, 2. 2, 3. That's it. And 3, 3. Okay. So that's all in there. Great. Let's just do one more with the same set. And again, we're going to do more in a second, but I want to talk about properties of these things. So how about this? Another set. Okay, we'll leave it a little bit shorter. We say x, y member of R prime. Another one. If x is less than y. Okay? And just to show you what this is, obviously they're going to be, this is less than or equal to y, this is less than or less than y. Just want to show you what this has, what this has that this doesn't have. All these are not in this relation. Okay, great. We're going to come back to do more examples. Let's just put down those things I asked you to. R, AR, S, AS, T. Okay? But I want to go through certain properties of, I shouldn't have erased that. That's okay. I wanted to go through certain properties of relations. So let's remember where we saw properties. We talked about functions. We talked about functions with special properties like one-to-one and onto. So now we're talking about relations, and I want to talk about special properties of relations. We're going to talk about 5 different properties that some relations have. And when I say relations, I mean relations of a set to itself. Okay, so we're only talking about S cross S, not S cross T. Okay? And so these 5 properties are as follows. Okay, and once we have the 5 properties, I'm going to go back on this list and show you what these, which one of the relations have these 5 properties. So again, for functions we had 3 properties. We had one-to-one, onto, and one-to-one correspondence. Here we're going to have 5 properties. Let's go through the 5 properties. The first property is R, for reflexive. I can do this without you. Okay, so here's the 5 properties. I wrote them out because we don't, because we want to go through them. Okay, reflexive. Reflexive means that every single x in S has the following property. X is related to itself. X comma X is a member of R. Okay, next, anti-reflexive. That says for all x, we can use this notation now. That's one of the benefits of doing these quantifiers. For all x, x comma X is not a member of the R. Okay, so we're going to see that most of the time, if you're reflexive, you're not anti-reflexive. If you're anti-reflexive, you're not reflexive. But you can be neither. You can't be both. Okay. Next, symmetric. So reflexive is, are you related to yourself? Anti-reflexive is, reflexive means every single person, every single thing is in the set S is related to itself. Anti-reflexive means for every single thing, you're not related to yourself. And we'll see this in a second. Okay? Symmetric. for all x, for all y, x comma y is a member of R. If x is related to y, then y is related to x. So that's a nice relation. Okay, x comma y is a member of R. That means y comma x is a member of R. So that's very nice. Antisymmetric says for all x, for all y. Okay, this is a little bit hard. This is a strange one. Okay, we always have the hard one. This is the hard one. The rest are easy. It says as follows: if x is related to y and y is related to x, sounds like symmetric to me, but it says if x is related to r, y, and y is related to x, then x equals to y. In other words, the only way you're going to have two things related to each other is if one is related to if x is related to y and y is related to x, then they must be equal to each other. Okay, we'll see examples of this in a second. And finally, transitive. Transitive as in trains, as in trans, you're going. It says as follows: if x is related to y and y is related to z, then x is related to z. Think about going on a train. If you can go from point x to point y on a train, and you can go from point y to point z on the train, then you can go from point x to point z on the train. Okay, and we'll go through this very carefully. Okay, so let's go through it. You ready? Let's do the simple one. X comma y. If x comma y is in R, if x is a sibling of y. Question. This is a nice relation. Is this relation reflexive? Yes or no? Okay? And we're going to ask this question for every one of these. And the answer is it reflexive? In other words, is every single person their own sibling? Are you your own sibling? And the answer is no, you're not. Okay, what's a sibling? A sibling is someone who's like that. Okay, someone who's well, you're not your own sibling. Your brothers are your siblings and your sisters are your siblings. Anti-reflexive. Is it anti-reflexive? Okay, is every single person not their own sibling? And the answer is yes. Okay, great. Is it symmetric? Okay, if I'm siblings with that person, is that person necessarily siblings with me? Answer is yes. Is it anti-symmetric? Let's see. If I'm siblings with this person and this person's siblings with me, does that mean that we're the same person? No. Okay, now we'll see. I told you the relationship between reflexive and anti-reflexive. If you're one, you're not the other. But the relationship between symmetric and anti-symmetric is a little bit more complicated than that. Great. Next. If I'm siblings with that person, and that person's siblings with the next person, am I siblings with that person? And the answer is yes. By the way, this doesn't necessarily work with half-siblings. Okay, what's a half-sibling? I share a mother or a father. Well, it's not transitive then. Okay, let's go through it. I could be half-siblings with someone. We can share the same mother. That person could be half-siblings with them, with the other person, with Z. They can share the same father. Then my relationship with Z is absolutely nothing. Okay, I have no relationship with them, whatever, other than saying he's my half-sibling, but there's no relationship. Okay, so this relationship is anti-reflexive, symmetric, and transitive. We're going to do it for all of them. Ready? Reflexive. Okay, X is dating Y. Okay, can you date yourself? You see, I can't run this class without a classroom full of guys that I can make fun of. It just doesn't work. Okay, sorry. Okay, but we're going to suffer through this. This is part of the problem, so it's going to be a little bit boring. Okay, can you date yourself? Answer no, you can't date yourself. You have to date someone else. Okay, is it anti-reflexive? Yes, it's anti-reflexive. Okay, is it symmetric? If X is dating Y, does that mean Y is dating X? I'd like to think so. In a moral world, it would be. So let's put a yes there. Okay, but I know some guys who did some pretty nasty things in their lives. Is it anti-symmetric? Okay, let's go through what anti-symmetric means. It says, if X is dating Y and Y is dating X, does that mean X is equal to Y? And the answer is no. Okay, two people can be dating each other. It doesn't mean that they're equal. Now, you see old married couples, they start looking like each other, but that doesn't mean that they're equal. Next, T, transitive. If X is dating Y and Y is dating Z, does that mean X is dating Z? No, usually X hates Z. So we're going to hope that doesn't happen. Okay? So X is dating Y and Y is dating Z. Does that mean X is dating Z? No, it doesn't. Okay, good. Let's do this one. R is U.S. citizen. R is a subset of U.S. citizens cross U.S. citizens. X, Y is a member of R if X and Y live in the same state. Okay? They live in the same state. Question. Let's go through it. I didn't put the parentheses here for no particular reason, just I ran out of space. Great. Is it reflexive? Do you live in the same state as you? Okay? And the answer is yes, it is. Okay. Is it anti-reflexive? Do you not live in the same state as you? Well, if it's reflexive, it's not anti-reflexive, so it's that. Great. Next, if X lives in the same state as Y, does Y live in the same state as X? The answer is yes. Great. Let's go through next. Antisymmetric. If X lives in the same state as Y and Y lives in the same state as X, does that mean X is equal to Y? Are you the same as every New Yorker? And the answer is no. By the way, so far we haven't seen one thing that's antisymmetric. That's okay. Transitive. Let's go through transitive. If X lives in the same state as Y and Y lives in the same state as Z, does that mean X lives in the same state as Z? And the answer is yes. Let's say that again. If X lives in the same state as Y and Y lives in the same state as Z, does that mean that X lives in the same state as Z? Yes. Okay? They all live in the same state. Great. Let's go through the next one. Okay? Less than or equal to. Okay? Let's go through this. Is X less than or equal to X? We're doing with reflexive. Is X less than or equal to X? And the answer is yes. It's equal to X. Great. Is it anti-reflexive? Is X not less than or equal to X? No, it's not. Okay, great. Question. If X is less than or equal to Y, does that mean that Y is less than or equal to X? No. 1 is less than 3 doesn't mean that 3 is less than 1. So it's not symmetric. Okay, great. Let's talk about antisymmetric. If X is less than or equal to Y and Y is less than or equal to X, what can you say about X and Y? Let's go through that again. If X is less than or equal to Y and Y is less than or equal to X, what can you say about X and Y? The only thing you can say is that they're equal. That's this. So it is antisymmetric. In fact, I could say the definition probably came from an example like this. Okay, finally, let's do transitive. Let's see what it says. If X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. So it is transitive. Great. Now here's the same one, but instead of or equal, we just have less than. Okay, now let's go through it. Okay. Is it reflexive? Is X less than X? Answer, no. Is it anti-reflexive? Is X not less than X? Yes, it is. That's correct. Next, is it symmetric? If X is less than Y, does that mean that Y is less than X? I'm sorry, I'm talking a little bit fast there for no particular reason, but you're on YouTube, you can stop, you can back up, you can listen to it again. Let's go through that again. If X is less than Y, does that mean that Y is less than X? Okay, and the answer is no, it doesn't. 2 is less than 3, 3 is not less than 2. Antisymmetric, let's go through antisymmetric. If X is less than Y and Y is less than X, how could that be? Hold on, let's go through this. This one is complicated, so we're going to go through this. If X is less than Y and Y is less than X, okay, then that's an arrow, it implies that. Now, when is that true? X is less than Y and Y is less than X? It's never true. And you can never have two numbers, X and Y, such that X is less than Y and Y is less than X. Doesn't make sense. So this thing is false. Okay? okay, here we get into trouble here. This is false. And what we say is false implies x is equal to y. You know what? That's true. False implies anything is true, so that's true. Okay, you have to go through that 3 times to understand that. But the main point is, whenever you have an arrow, if the beginning of the arrow is totally false, then the arrow is true. Okay, finally, let's do transitive. If x is less than y, and y is less than z, is x less than z? And the answer is yes. Okay, so that's 1, 2, 3, 4, 5 different examples. We're going to do some more examples. Okay, but that was very nice to go through them. Okay, great. Let's go through some more examples. I'm going to leave the definitions of the relations here because we're going to use them again and 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 again. Okay, especially when we do homework, we're going to need them also. Okay, let's do another one. Okay, R, subset of the natural numbers cross the natural numbers. Okay, and we have as follows: x comma y, member of R. 2 numbers are related to each other if and only if, I shouldn't have done if and only if, the book doesn't do that, if x is less than or equal to y plus 5. Okay, okay, great. Okay, so now let's ask the following question. Is it reflexive? Is it anti-reflexive? Is it symmetric? Is it anti-symmetric? Is it transitive? Okay, let's go through these very carefully. Is it reflexive? Is x less than or equal to x plus 5? And the answer is absolutely yes. Is it anti-reflexive? And the answer is absolutely no. X is not less than y plus 5? X is not less than y. X is not less than x plus 5? No, x is less than or equal to, it's less than x plus 5. Okay, great. Let's go through this. Question. If x is less than y plus 5, does that mean that y is less than x plus 5? Let's go through that again. If x is less than or equal to y plus 5, does that imply that y is less than or equal to x plus 5? Yes or no? Okay, let's plug in some numbers. Okay, if 3 is less than or equal to 10 plus 5, that's a true statement. 10 plus 5 is 15, 3 is less than 15. Does that imply that 10 is less than or equal to 3 plus 5? 10 is less than 3 plus 5 is 8. 3 plus 5 is 8. This is true, this is false. So we cancel it out. We cross it out. So this is a false statement. Okay, great. Okay, let's try another one. Let's try anti-symmetric. It gets a little bit more complicated here, but the answer is, let's do this. 3 is less than or equal to 4 plus 5. That's true. 4 is less than or equal to 3 plus 5. 3 is less than 9, 4 is less than 8. Both of them are true. Okay? Question, so this is true and that's true. Does this imply that 3 equals 4? No, it doesn't. No, it doesn't. 3 does not equal to 4 just because that's true. Okay, so it's not, I wrote false, I meant x. Okay, that's not. Question, is it transitive? Let's see what it says. Is it transitive? And the answer is no, it's not transitive. And I'd like to show you why it's not transitive. That takes a little bit of thought, but we can do it. It goes as follows. 10 is less than or equal to 5 plus 5. 10 is less than or equal to 10. That's true. And, okay, 5 is less than or equal to 1 plus 5. 1 plus 5 is 6. 5 is less than 6. That's true also. Okay? Question. Does that imply that 10 is less than or equal to 1 plus 5? No. So this is, let's do it with a different color here. Hold on. This is X, this is Y, this is Y, this is Z, this is X, this is Z. Okay? And this is false, and this is true. False implies true is false. So that whole statement is absolutely positively false. Okay? So here we get into a little bit more complicated, but we're following exactly the definitions of these things, so it's a little bit easy. Okay? Great. Okay, let's do another one. Okay. The next 1, 2, 3 of them are a little bit just mind-boggling, but we're doing it so we can follow exactly the rules and we'll understand the rules much better. Again, not one example did the book do. Okay, so you're reading the book on your own and you're coming up with your own answers or your own examples. Okay, so let S be a set. Okay, and we're going to call a relation R on a subset of S cross is a subset of S cross S, and we have the following. This relation is defined as follows: X comma Y is a member of R if X equals Y. That's a funny one. Okay, in other words, everything is related only to itself. No element in S is related to any other element in S. They're only related to itself. Okay? We can write that as follows. Okay? Well, I don't want to write it. I want to talk about its properties. Is it reflexive? Is it anti-reflexive? Is it symmetric? Is it anti-symmetric? Is it transitive? Okay? Now we go through each one of them and we go through it. Question. What does this say? Reflexive. Every element is related to itself. Is every element related to itself? Absolutely. That's exactly what it says. Every element is only related to itself. Okay? Only related to itself, not related to anything else. Is it anti-reflexive? No, it's not. Every element is related to itself. Is it symmetric? Now be careful. Let's go through this. If X is related to Y, how could X be related to Y? They're the same element. Does that imply that Y is related to X? If X equals Y, does that mean that Y equals X? Yes, it does. That's exactly what symmetry is. Okay, next, let's go through it to this one. If X is related to Y and Y is related to X, does that mean that X is equal to Y? Well, if X is related to Y, that means X is equal to Y. So just this itself implies that they're equal. So yes, it's symmetric and it's anti-symmetric. Okay, so as I told you, with reflexive and anti-reflexive, if you're one, you're not the other. But here you could be both, symmetric and anti-symmetric. Okay, let's go through transitive. If X is related to Y, how could that be? Well, they're the same thing. Okay, and Y is related to Z. How could that be? They're the same thing. Okay, then does that mean X is related to Z? Well, if X is the same thing as Y and Y is the same thing as Z, then X is the same thing as Z. So that's true too. Okay, that's good. Okay, next. This is called the equality relation. Okay, two more. Okay, let's do this. R, a subset of S cross S, and R equals S cross S. In other words, for all X, for all Y, x comma y, shoot, x comma y is a member of R. In other words, everything, here we have, everything is just related to itself. Here we have, everything is related to everything. Okay? And so we do this, as well, this has a name, it's called the universal, good Lord, the universal relation. Everything is related to itself. I'm sorry, everything is related to everything else. Let's go through the properties. Reflexive, anti-reflexive, symmetric, anti-symmetric, transitive. Okay, let's go through it. Okay. Question. Everything is related to everything. Is that reflexive? Well, reflexive just says that x itself should be related to x. Well, x is related to everything. Y is related to everything. Z is related to everything. So is this true? Yes, it's true. X is related to everything, including x. Is it anti-reflexive? Anti-reflexive says something is not in there. So it's not anti-reflexive. Symmetric. If x is related to y, well, x is related to y. Does that mean that y is related to x? Does that imply that y is related to x? Well, everything is related to everything. So yes, it is true because the second thing is always true. Okay. Next, anti-symmetric. If x is related to y and y is related to x, well, everything is related to everything, so that's going to happen. Does that mean x is equal to y? Well, everything's in there. So no, two different things. One could be related to that, and that one's going to be related to that, but they're not equal. So that's different. Okay, and finally, transitive. If x is related to y, everything is related to that. Everything is related to everything else. And y is related to z, everything is related to everything. Does that mean x is related to z? And the answer is yes, x is related to z. After the arrow is always true, makes this arrow true. Okay, so we have that. Okay, notice in these two, reflexive, symmetric, and transitive is on. Reflexive, symmetric, and transitive is on. We're going to see that that's going to be an important thing in section 3.4. We're going to talk about that later. Next is again, where it's a strange relation, but we're going to talk about it because we want to go through all these properties very carefully. So you have a set S, you have pairs of elements, and you have the empty relation. You know what? Let's write that a different way. You have R, okay, and I want to describe R. R equals the empty set. In other words, there is nothing related to anything else. Okay, and now we want to go through and we want to ask, is it reflexive? Is it anti-reflexive? Is it symmetric? Is it anti-symmetric? Is it transitive? Let's go through it. Is it reflexive? Is every element related to itself? No, nothing is related to itself. Nothing's related to anything else. Is it anti-reflexive? Sorry, got to change colors. Hold on, don't move. Sorry, got to change colors. Okay, is it anti-reflexive? Well, again, nothing is related to anything else, and we want, for anti-reflexive, we want any object is not related to itself, so nothing is related to anything, so it's definitely anti-reflexive. I'm sorry, I made a mistake here. It's not reflexive. It's not reflexive. It is anti-reflexive. Is it symmetric? Well, watch. Look what symmetric says. It says if x is related to y, that's not true. X is not related to y. There's no pair of elements that are related. Therefore, this first part of the arrow is false. False arrow anything is true. False arrow false is true. So it's symmetric. Great, let's do this. This is again, take two things. Okay? They're not related. They're not related. So this is definitely false. Does that imply x is equal to y? And the answer is false arrow anything is true. So it's true. Let me just make sure that I have that right. Okay, good. And finally, transitive. Okay, this is a little bit strange. This is false and this is false. Does that imply this is false? I don't care. False and false is false. False arrow anything is true. So it's true. Okay, so that's a nice little example. Okay, great. Okay. A few more little concepts and we'll be finished this section. But it's a nice section. It's got a lot of nice problems. And these relations show up everywhere in computer science. They show up everywhere in computers. They show up everywhere in science. They show up everywhere in math. It's a very important concept. Okay, great. Okay, definition. Something just to keep your interest at the end of the hour, we'll do this in blue. Okay, let R be a relation on the set of S cross T. Okay, so let's just remember, originally we were talking about relations between two different sets. Then we focused on relations between a set, and we had these 5 properties. Now we're going back to the original thing. R is a subset of S cross T. There'll be a relation. Then the converse relation is written as follows: R back arrow subset of T cross S. So this is S cross T, this is the back arrow of that, is defined as, okay, we're making a definition, okay, T comma S is a member of R back arrow if and only if, or if and only if, okay, S comma T is a member of R. So two things are related if you can turn them around. I'm sorry, if you turn them around, if they're related here, they're related there. So basically this has the same information, it's just backwards. So here, let's say we were talking about customers and product, here we're talking about products and customers. It's not a problem. Okay, you could think of inverse functions. Okay, but that's kind of the same idea. Okay, so this is something, there's a lot of nice homework questions and we're going to talk about it when we want to do the homework. Okay, great. Great. Another idea. Let S be a finite set. Some of those sets we were finite, but sometimes we talked about the natural numbers. That's an infinite set. We have no problem with that. Okay? Okay. Let R be a subset of S cross S. Okay. We can make a graph. And by a graph here, I mean just a picture, dots and edges between them. Dots and edges between them. We're going to see a little bit more of this in section 3.2. Okay, so this is a very nice way of, you take a relation, you make a graph out of it, a picture. Okay, it goes as follows. Let's do it as follows. Okay, consider the following example. S is equal to 0, 1, 2, 3, 4, 5, 6. Okay, and then we have the following. R subset of S cross S. So this is numbers from 0 to 6. And we have, I'll tell you what the subset is. It says as follows: x comma y is a member of R if x minus y is even. Okay. Okay, we have to think about that. So let's go through this. Question: is 4 related to 2? Is 4 related to 2? So let's do this. 4 minus 2 is 2. Is 2 an even number? Yes, it is. 2 is an even number. So 4 is related to 2. Question: is 4 related to 3? 4 minus 3 is 1. 1 is an odd number. It's not related. 4 is not related to 3. Okay, let's do this. 6 related to 1. Let's do it. 6 minus 1 is 5. Is 5 even? No, it's odd. Okay, so what I'd like to do is draw a picture of this relation, a graph. So I'm drawing a graph of this relation. Okay, and the objects of the graph the nodes of the graph, and again, I know you know what a graph is. We're going to see more about graphs next section. Let's do it. The objects of the graph are the elements of S. So we can write it as follows: 0, 1, 2, 3, 4, 5, 6. Okay, and then we do as follows. Okay, we do as follows. If one node is related to another node, then we draw an edge. So what did I say? I said 4 is related to 2. Okay, let's ask the following question. I said 4 is not related to 1. Let's ask the following question. Is 4 related to 0? Let's go through it. 4 minus 0 is 4. 4 is an even number. Question: is 2 related to 4? Is 2 related to 4? Let's go through that. 2 minus 4 is negative 2. Is negative 2 an even number? And the answer is yes, it is. Okay? And is 0 minus 4 an even number? And the answer is yes, it is. Okay, let's do 5 and 3. Is 5 related to 3? 5 minus 3 is 2. They're related. Is 3 minus 5 negative 2? In fact, every time we're going to have, in this relation, every time we have one way, we have the other way. Let's see why. X minus y is equal to y minus x with a minus in front of it. If this is even, then this is even. Okay, so let's do it. 6 and 5. Is 6 related to 5? Answer: no. 6 minus 5 is 1. 1 is odd. Is 5 related to 6? No. 5 minus 6 is negative 1. But 4 is related to 6, and 6 is related to 4. And 6 is related to 0, and 0 is related to that. And 6 is related to 2, and 2 is related to 6. And 2 is related to 0, and 2 is related to that. Okay? Great. And 1 is related to 3, and 3 is related to 1, and 1 is related to 5, and 5 is related to 1. Okay. By the way, we can see, oh, hold on, I'm not even finished. Question: is 0 related to 0? Yes, it is. Because 0 minus 0 is 0, which is even. 2 related to 2. 2 minus 2 is 0. 4 minus 4 is 0. 6 minus 6 is 0. 5 minus 5 is 0. 3 minus 3 is 0. 1 minus 1 is 0. Okay. By the way, let's write down what properties this has, and then we're going to see if we can see those properties inside this function. Okay, so let's go through them. Are anti-reflexive, symmetric, anti-symmetric, transitive. Okay, let's go through it. Is it reflexive? Yes. Why? Because is x always related to x? Answer: if x minus x is even. Is x minus x even? X minus x is 0. 0 is always even. Conclusion: it's reflexive. Okay, what does that show in reflexive? Well, very simple. Every single dot has a little circle on it because every single thing is related to itself. It's pointing to itself. Great. Is it anti-reflexive? Answer, no, because everything is related to itself. What type of graph would be anti-reflexive? Answer, it wouldn't have these little self-loops. These are self-loops. If all the nodes do not have the self-loops, then they're not related to each other. Then it's anti-reflexive. Okay? Question, is it symmetric? What does it mean to be symmetric? It means if there's an arrow this way, then there's an arrow this way. What it says is if x is related to y, then y is related to x. Okay? Well, I showed you this is symmetric. So it is symmetric. It does have this property. Whenever there's an arrow one way, there's an arrow on the other way. Okay? Is it anti-symmetric? Let's see. 2 is related to 4, and 4 is related to 2. Does that mean 2 is equal to 4? No. Okay? And finally, transitive. What does a transitive mean? Transitive means that if there's a way of going from one place to another place, and there's a way of going from the second place to the third place, then there's a way of getting to all that. In other words, somehow if you can travel through a local, does that mean you can get there by express? Anyways, the answer in this case is yes. But you can see it like this. By the way, I'd like to draw this a little bit the same way, the same graph, but a little bit, knowing that this is a symmetric graph, then why draw it like this when we could draw it like this? X, Y, and just draw a single line without an arrow, without a tip. Okay, if we do that, then this graph becomes this graph. Sorry. 0, 2, 4, 6. Okay. Okay. And this is 1, 3, and 5. It's a little bit simpler. Oh, but don't forget your little loops. That's nice. Okay. Okay. And I just want to show you what transitive means. Transitive means that if you can go from here to here, and you can go from here to here, then you can definitely go from here to there. So you can see these relations in terms of this graph. So again, given a graph, and here I mean graph by graph theory, given a graph, given a relation, you can generate a graph. Given, you can tell the properties of the relation by looking at the graph. Okay, so that is the end of section 3.1. Okay, let me just tell you what section 3.2 is about. It's about graph theory. We got into graphs by talking about this. We're going to go into graph theory. And again, a graph is a way of, really a graph is just expressing a relation. So we're going to talk about that. Okay, good night.